Hello. In this video, we will discuss 3 additional reactions besides the 5 electrophilic substitution reactions that have been the main focus of this chapter so far. Let me remind you, in each of those reactions, we replace a hydrogen on a benzene ring with some other group, a sulfonic acid group, an alkyl group, an acyl group, nitro, or halogen. In these 3 reactions I will introduce you to today, we are taking groups that are already on a benzene ring and modifying them into other groups. Specifically, we'll learn how to turn a nitro group into an amino group, how to turn an alkyl group into a carboxylic acid group, and how to turn an acyl group into an alkyl group. Let's start with side chain oxidation. This is a reaction you've already learned, and let me remind you, it's on page 815 if you wish to refer to that reaction. It involves taking an alkyl group and chewing it down to the end to a carboxylic acid group. As an example, an N-propyl group on treatment with either Jones reagent or K-amino4 potassium permanganate. It's generally done in base. The product will end up being a carboxylic acid. That's an important reaction because it's one of the, there are several ways, but one of the important ways of introducing a carboxylic acid group onto a benzene ring. The reaction will occur more than once if there are several alkyl groups on the benzene ring. Oftentimes we'll use toluene as a starting material because it's very much available. That is a methyl group on the benzene ring. If there are hydroxy groups on the benzene ring, it won't work because, as you remember, generally those will get oxidized to quinones. And one further case where it won't work is if the alkyl group is tertiary, treatment with K-amino4 or Jones reagent. I'll just vary it by using Jones in this case, no reaction occurs. And that's because in order for a oxidation to occur at the carbon next to a benzene ring, there has to be at least one hydrogen on that carbon. So it won't work with tertiary groups, but any other alkyl groups it will. The second of the 3 reactions we will be learning today is a name reaction. Actually, it's 2 different ones, but they both accomplish the same thing. It's the Clemmensen Reduction or the Wolff-Kishner Reduction. In both of these reactions, a benzene ring with a ketone group, where the C-double-bond-O is directly attached to a benzene ring, or for that matter, really any ketone group, but it's particularly useful when we're talking about acyl benzenes, the reason being that these are directly available through Friedel-Crafts acylation, in which you put on the acyl group. But if you already have an acyl group on the benzene ring, you can treat it with a compound called hydrazine, which is N2H4, kind of like ammonia, but not exactly. This is N2H4, and concentrated sodium hydroxide. Essentially, the double bond O disappears and becomes a CH2 group. This is what's called the Wolff-Kishner reaction, or alternatively, you can use what's called the Clemmensen reduction. And that involves zinc, metal, and concentrated hydrochloric acid. That accomplishes the same thing, converts the C-double-bond-O into a CH2 group. A couple things about this reaction. Why would you want to do it? Typically, you don't want to take a perfectly good functional group and turn it into something that doesn't have that functional group there. The chemist's job is generally to elaborate more and more functional groups, not less and less functional groups in a molecule. And yet this is a very useful thing to do because, as you remember, it's very difficult to introduce an alkyl group directly onto a benzene ring because that involves Friedel-Crafts alkylation, which, as you remember, has 2 problems. First of all, it undergoes rearrangement, so it's very difficult to get a primary alkyl group on a benzene ring. And secondly, it involves over-alkylation, in which you may put more than one group on. So if you want to attach one alkyl group to a benzene ring, particularly if it's primary, the thing to do is first acylate it, which you may remember has none of those problems, and then do a Wolff-Kishner or a Clemmensen reduction to turn the double bond O into a CH2 group. Okay. Notice also about these 2 reactions, why do we have to learn 2 when there's either one of them will work the same way? Well, notice that this is done with concentrated base, so if you have a functional group elsewhere in the molecule which might be sensitive to base, you don't want to use this reaction. Instead, you'd use this one, which uses concentrated HCl. But if you had a group somewhere in the molecule that was sensitive to acid, then you wouldn't want to use this one, you would use this one instead. So they serve as complementary reactions In some cases you might want to use one, in some cases the other, or sometimes either one will work. Again, this is converting one kind of group on a benzene ring to another kind of group, just like we saw in the last case where we converted a alkyl group to a carboxylic acid. Notice that that could follow with this. You can convert this directly to carboxylic acid using that side chain oxidation reaction. And then the third reaction set is the reduction of a nitro group to an amino group. As you know, you can introduce a nitro group directly onto a benzene ring, but you can use a nitro group and reduce it with iron, that's iron metal, and concentrated HCl, or you can use tin metal and concentrated HCl. Sort of like in the last example, we used zinc metal and concentrated HCl to turn a double bond O into a CH2 group. In this, we're turning a nitro group into a NH2 group. Again, this is a reaction that converts a group that you can directly introduce onto a benzene ring into another group that is more difficult to introduce directly onto a benzene ring. So you do it indirectly through a nitro group and convert it into an NH2 group. None of these reactions that we've learned today will we need to know mechanisms for, because in fact all three of them are redox reactions. Just to be clear about it, the first reaction, where you convert an alkyl group into a carboxylic acid, that's an oxidation, the oxidizing agent being chromic acid in the case of the Jones reagent, or permanganate in the case of the KMNO4 reaction. The second and third ones were reductions, in which the reducing agent is a metal, tin, iron, or in the second reaction, zinc. Remember, metals, not ionic compounds, but the metals themselves are reducing agents because they want to give away electrons. That's what makes them reducing agents. And so the second and the third reactions are reductions. The first reaction was an oxidation. Thank you for your attention.